Hey there.
Hi,
How are you?
I'm good. How are you?
I'm good. So yeah, I sent you an email about that beetle problem. So it was just that if you're crossing two red beetles, um, you need to figure out the probability for both of those.
Yeah.
So yeah, did that make sense?
Yes, it does.
Okay, cool. All right. What would you like to go over today?
Yeah, so I found a problem on like Archimedes principle of buoyancy things.
Huh?
So we can go over the problem and I guess
Sure.
yeah, those concepts.
Mhm. Okay. All right. Why don't
Yeah.
you start off by how
Yeah.
you approach this?
Um so I just did this. I haven't really had much time to uh so they are giving me the volume of the marshmallow
Yeah, do you remember what
and
the cubic centimeters were?
yeah, it's equal to a milliliter.
Good. Do you remember how like how many liters are in a cubic meter?
Yes, 1,000 liters.
Good, good, good. Okay, cool.
Um, yes. So they're giving me the volume of the marshmallow and
Mhm.
the volume of the hot chocolate, and their respective densities. And they want me to know what percentage of the marshmallow is above the hot chocolate.
Mhm.
Um, and of course, gravity, and I should ignore atmospheric pressure.
Mhm.
So the way I started thinking about this was in terms of like forces acting on it. So like a force from like the marshmallow down, and I guess gravity is what I thought. And then an upwards force from opposite of this, of like the hot chocolate, like
Yeah.
against the marshmallow.
So the buoyant force, right?
Yes, the buoyant force.
Okay. Now, yeah, so yeah, I would do the same. I would draw like a picture. So let's say this is like the hot chocolate here, and Um, oh well, they're asking what percentage of the marshmallow is above the surface. So this is not going to be completely submerged. So I'll just draw it kind of like this. And then, the gravitational force going down, buoyant force, going up. And what else do you remember about? So like the gravitational force would be mg, right? Right?
And I guess I could use density times volume times G.
So I just want to make sure. So the force of gravity the is equal to like mg, right? Does that make sense?
Yes.
Okay. Um, and the buoyant force, do you remember what that would be equal to?
No, I don't remember.
So yeah, so this would be so Archimedes' principle or law states that an object submerged in a liquid, um, or partially submerged, will displace its own volume or part of its own volume in the liquid of the fluid. So that would mean that so yeah, so the buoyant force would be equal to rho, which is the density. Um, and it's the density of the so it'll be rho of the um density of the object and volume of the object, or rather volume, yeah, of the fluid that's displaced times g.
I think I always get confused on like which density and which volume. Could we go over that again?
Sure. So since we're talking about um so the buoyant force, that's going to be the force that is caused by the fluid. So that density value is going to be the density of the fluid
Okay.
because
And
that's yeah.
the volume here is the volume of the fluid as well.
Hmm. Yeah, it's the volume of what's displaced. So like I guess like a simpler example would be like if something is completely submerged, because here, let's say the force of gravity is the mg, the buoyant force is rho of the fluid, volume of the fluid displaced, and then g. Now, if something is completely submerged, that means that the object's entire volume is submerged, and if its entire volume is submerged, it must displace that equivalent amount of volume of the fluid, right?
Okay.
You remember, like, I don't know if you did this in like, I just remember in like eighth grade or something, we have like a graduated cylinder, and let's say this is like 10 milliliters or something. You take like a rock and you throw it in, and then the new level, let's say, is like 13 milliliters. You know that the volume of that rock that you threw in is going to be 3 milliliters, right?
I see.
Mm-hmm.
So I see. So
Mm-hmm.
so that volume will always correspond to what's being submerged.
Yeah, because what's being submerged will displace that same amount of the fluid.
I see.
Mhm.
Okay, I see. So I feel like um
Mhm.
yeah, yeah, it's becoming
Yep.
a bit more clear, yeah.
Hmm.
So
Yeah.
in this problem, we're going to have to sort of um find V to have that percentage.
Uh-huh.
Mhm.
Yeah. So what we can do is so rho what would the unit for this be? Rho V, V being volume.
Density times volume.
Mhm.
I guess
Just exactly.
isn't it just, don't we just use density times volume to find mass?
Yep.
So like grams.
Hmm. Hmm. Good. So the reason I asked is because this gravity term, mg, we can turn that into rho of the object, right, times volume of the object times g.
Yes, I see that.
Hmm. So, so this thing over here, um, yeah, that will help you realize that, the density of mass over volume. So if you're multiplying it by volume, you get mass, and vice versa. We can take the mass value. Um, so yeah, something to remember is just that a buoyant force is a consequence of um the fluid being displaced. So it's the fluid that's producing the buoyant force, whereas the gravitational force is just acting on the object with mass. So that's why we typically draw or write the weight of an object as mg, and the buoyant force will be essentially negative. Well, it will be equal to negative mg or negative weight, because it really what it does is it displaces its own weight, something that's submerged. So, so yeah, be able to yeah, so first things first, for the buoyant force, that's fluid. And the volume is fluid displaced. So you have that. And then you have, in your free body diagram, the mg, and you want to figure something out where, because they don't give us the mass of the object, but they do give us the density. And so we can rearrange or we write mg as with a density term in it, right?
Yeah. Yeah.
Okay. Now, um, okay. So now what can we do from here?
Hmm.
What's the net force here?
The net force. So like if if you add all of the forces acting on it,
Mhm.
so like the buoyant force plus the gravitational force,
Uh-huh. Would that net force be like,
it
uh-huh.
has to balance each other out, and that's why it's floating, is my guess.
So the net force would be what?
Zero.
Yep. Because so Newton's second law. What's Newton's second law?
Uh, is it like the opposite reaction one?
Nope.
No.
No. It's the one that's like a formula.
Mass times acceleration, force is mass times acceleration.
Yeah, so it might so we think of it this way, but I want to make sure that the force here is really the sum of all the forces, which means net force. So what that means is for so yeah, so what that means is that it's the sum of all the forces. So we're going to add the two forces. And since they're in opposite directions, one will just be a negative. So we can rewrite this as like
One
force,
equals the other.
yeah,
Mhm.
let's say like force of gravity minus force of the buoyant force. It could also be the other way around, just, depends on wherever you put the negative term, is equal to ma. Now, so the best way to I guess, conceptualize Newton's second law and why it's so important is what it states is that if there is a net force on something, there must be an acceleration, and essentially vice versa. If something has an acceleration, it means that it's experiencing a net force that's, not zero. So for this marshmallow thing, it's floating. It's not, going down or up. I mean, even in this example where I drew something submerged, I drew it like when it's stationary there, submerged. So yeah, so we have no acceleration. So an acceleration zero. So then this is zero, right? And then we can just subtract or rather add buoyant force on both sides to get this, right? And then we can plug in the values that or the expressions that we made that have the density terms in there. So density of the object, volume of the object, that's really volume of the object that's submerged, times G is equal to rho of the fluid, volume of the fluid displaced, times G, right?
Yeah.
Okay. What can we do here?
We can, well, we have, so we can just solve for volume of the fluid displaced.
Yeah. So we can get rid of the G's first, right?
Yeah.
Uh-huh. Okay. Now, for the next step, you said we can find what?
But we can solve for volume of the fluid displaced.
Yep. So I'm going to erase that. So that's going to be, so volume of the fluid displaced is going to be equal to what?
It's going to be equal to density of the object times volume of the object over density of the fluid.
Good. And um, and they give us the information for that, right? So we have
Yeah.
the object. So the object is going to be what in this case?
The marshmallow.
Yep. So this will be 0.5. grams per milliliter, and the volume of the marshmallow is 20, it's cubic centimeters, which is equal to a milliliter. So I'm just going to
Mhm.
write 20 milliliters
Yeah.
divided by the density of the fluid, which is 1.1 gram per milliliter. So up top, this becomes 10 grams. On the bottom, it becomes 1.1 grams per ml.
Yep. And
And
then grams cancel out. So we'll have like 10 point around 10 milliliters.
yep, let's say like, yeah, let's say like maybe like, I don't know, let's say like 9 or something, just because it'll be a little bit less than 10, but yeah, that's the idea. So okay, that's the volume of the fluid that is displaced. And what we need to find is what percentage of the marshmallow is above um, the surface of the hot chocolate.
Oh, I see. So that's the volume that's displaced. And the volume that's displaced ideally would have been the complete volume. So like the 20 mLs kind of. So
Okay.
like so
Mhm.
that's why it's around half. I get it. I think it's because like it would have been 20 centimeters if it were fully displaced, but only about 9 milliliters was displaced.
Uh-huh.
So that means that like only about 9 cubic centimeters of the volume
Mhm.
was displaced.
Yeah. So yeah, roughly 9, milliliters is the volume of the fluid displaced, which is equal to, so I should also say that, volume of fluid displaced would be equal to the volume of the object that's submerged. So, so if 9 milliliters is how much of the object is submerged, right? It
Yeah,
means that the part that isn't submerged is the rest of that 20 mLs. So that'll be like the 11 mLs or whatever. But
I see.
basically, the 1.1 just shows you that more than half would be above, or rather, sorry, more than half would be, or sorry, less than half would be submerged, and more than half would be uh not submerged. So that's
I
why
see.
it's the 55%, but they could have made this like a 45% answer choice, and I think that would have been a good way to trick you because what they're asking for is above the surface, right? But it's easy to make the mistake of putting in the answer that is below the surface. So that's the way that they could have made this harder. But yeah, so essentially what you're doing here is, you start with your free body diagram. You draw the forces that free body is experiencing, and remember that, yeah, remember this, like that's Archimedes' law for the buoyant force. So remember, yeah, it's a consequence of the fluid. So it's rho fluid, volume of the fluid displaced times g, and then when you're dealing with the gravitational force, you should be able to turn that mg into density of the object times volume of the object that's submerged. Yeah.
Okay,
Mhm.
I got it. Sounds
Yep.
good.
Yep.
No, that was quick for us. We usually
Yeah,
take a
yeah.
lot longer.
Yep.
Um, I guess the other thing that I've been really drilling
Mhm.
um has been like physics and organic chemistry
Yep.
in UWorld. And yeah, we can go over part of this passage. But more broadly, like carboxylic acid derivatives, and I think this one is like lactams and like cyclization. It-
Okay.
yeah,
Yep. So why don't you, yeah, you can start reading this.
it's going to hurt. not very confident in order. So the beta-lactam scaffold is an important feature in a class of broad-spectrum antibiotics that includes penicillins, the cephalosporins, and monobactams. So I know that a scaffold is that like I think it's like a is I'm thinking of like a chaperone protein, like something that helps things structurally be where they should be.
Hmm.
That's my thought here.
Hmm.
I don't
Yeah,
know.
it's
And
like
it's a
that.
lactam. That's all I
Oh yeah. Do you remember what?
Isn't it not this? Like the, or am I confusing it? Like a ring with
Go on.
like this is what I'm imagining when I'm thinking of a lactam ring.
Uh-huh. So what about that?
Like an amide.
Yeah, yeah.
No.
So yeah. So lactams will have that amide um group. So yeah, you have the double bonded carbonyl and then the nitrogen there. So good. Do you remember what
Uh,
it was?
sorry.
Do you remember what a lactone was?
It's the same, but with carboxylic acid or an ester, one of those two.
Yeah.
Uh, Probably an ester.
Yeah, it would be if
Yeah.
this was just an oxygen here. So, all right, good. So, oh, and then you something about like a scaffold.
Yes.
Okay. And what were you saying about that?
My thought of it is like something that's helping, a protein that's helping, sort of like a chaperone protein of like something structurally where it should be. That's my thought.
Uh, yeah. I think the chaperone, well, maybe I'm only thinking about the heat shock or the thing that prevents it from heating up, but yeah, yeah, you have the idea. It's essentially some type of structural support. So, okay, cool. Then they say the penicillins work by inhibiting a step in the synthesis of peptidoglycan. Do you remember that? Peptidoglycan?
Yeah. So it's a bacteria cell wall has peptidoglycan.
All right. Do you remember which type had like a thick peptide, like out of the two types of bacteria? Mhm.
No.
So,
Yeah.
so the gram positive, gram negative, that those names are given based on how much of like a pink, I think, or purple dye is taken up.
Saffron red, yeah.
Yeah, yeah. So, um, and so the peptidoglycan is what takes up that like stain or the pigment or whatever. So gram positive would be the one that has the thick peptidoglycan cell wall, and gram negative would have a thin peptidoglycan cell wall, so it's not going to stain as, purple, or it'll be like more pinkish. Um, but gram negative bacteria, in addition to the thin peptidoglycan cell wall, they also have an outer membrane.
Yes.
Mhm.
I think I remember that that is why they're not staining
Yep.
because they have this outer membrane that they when they do the wash, dye rinses off. Like it never penetrates into the cell wall.
Yeah. And I think it also could have something to do with just how, because I think the peptidoglycan is the thing that takes the stain, and if they have a thin cell wall of peptidoglycan, that can be a reduction in how much is taken up. But but yeah, it could probably be both of those things. But okay. And then they're saying, however, the development of antibiotic resistance in the form of enzymes such as beta lactamase is a growing uh problem. Okay. So antibiotic resistance and then this type of enzyme. Okay, continue.
An aromatic ring linked to the beta lactam ring has been reported to participate in hydrophobic interactions with beta lactamase active sites. and an aromatic ring bonded to the nitrogen atom of the beta-lactam has shown to be beneficial to biological activity.
All right, what are they saying here?
Um, so there's an aromatic ring here, or here
Uh-huh.
that's linked to this lactam ring.
Okay.
Um, and it's hydrophobic. So this hydrophobicity helps it bind to the active site
Okay.
of this enzyme.
Good.
Uh,
Mm-hmm.
yeah. So I guess there's actually two aromatic rings,
Yeah,
which
the one
here.
that's bound to the nitrogen atom, so far they're just saying it's beneficial to biological activity, but we don't know how yet. But what we do know is the ones that are not linked to the nitrogen atom cause it to be more hydrophobic, and the beta lactamase enzyme, its active site is hydrophobic, so it can work as a substrate there.
Yep.
Mhm.
Researchers synthesized a group of penicillinic acid analogs with substituted aromatic rings bonded to both the carbon scaffold of the beta-lactam ring and to its nitrogen heteroatom to overcome the challenge of antibiotic resistance.
Okay.
So they're making synthetic analogs of this
Mm-hmm.
with aromatic rings that are substituted. So that means that they have like other groups bonded to it.
Uh-huh. And where's the oh, okay. Never mind. So yeah, good.
Okay. To overcome the challenge of okay, I see. So that they're adding these groups so that it can't add to like the active site of beta lactamase probably,
Mm-hmm.
and like preventing this. Uh, so they're challenging like the hydrophobicity of it. I guess it's my interpretation,
Yeah,
so that it doesn't bind to the active site. Yeah.
yeah. So it might also just be um too big, like because they're saying that like so okay, so we know that when we have aromatic rings that it would become more hydrophobic, and if it's more hydrophobic, it's better able to be a substrate for this enzyme. But now they're saying that they're using substituted aromatic rings, which would be the aromatic rings that have, R groups attached to it. And that's seems like they're saying is something that they're doing to overcome the challenge of antibiotic resistance. So my guess is maybe that causes too much steric hindrance for the enzyme, but not sure yet. But yeah, you can continue.
Various substituents, including OCH3
Oh,
and
sorry.
sorry,
Oh, yeah.
um, and NO2.
Mhm.
I see. Um, so probably, I guess I'm thinking here of like if this is another CH3 of like an ether or like
Mhm.
an amide, or utilized as groups R1, R2, R3 to make several analogs.
Okay.
An overview of the synthesis of these analogs is shown in Figure 1, where the key step is a coupling of compounds 2 and 4 driven by DCC to form a compound with two linked beta-lactam rings. This is DCC. This is compound 1. Okay, it's weird how they have it here.
Oh,
But
yeah.
yes, this is a synthesis.
Yeah. Okay. So they're talking about, so okay, the R groups here are like, I thought they were just going to be big carbon chains, but it seems like there's things like OCH 3 and the nitrite thing. Now, what do you think those do?
Here,
Oh, I just mean, so the R groups they said were these things.
yeah. my thought is that it would make them less hydrophobic initially, but these are not really, are they?
Yeah, maybe
They
they.
have polar groups, so I don't,
Okay, okay. Go
that's
from
my thought.
yeah, continue that thought.
Um, can I know that they can withdraw electrons because they are polar groups,
Yeah,
but
they're
like,
electron withdrawing groups, right?
yeah,
And what those do is they pull electron density towards themselves through the inductive effect. Okay, now they're telling us that okay. Uh, Overview of the synthesis of these analogs in figure 1, where the key step is the coupling of compounds 2 and 4 driven by dicyclohexyl carbodimide. So look at to form a compound with 2 linked beta-lactam rings. So I would first just look at compound 1 here, and they're adding lithium hydroxide um, and to get compound 2. So what's happening there?
yeah. So this is getting you're going from a methyl group to the hydrogen. So you're hydrating the carboxylic acid.
So tell me a little bit more about how that changes.
So I guess the
So what changing seems to be in compound 1, we have an ester, right? And compound 2, we have just a what?
carboxylic acid.
Yep. So what would cause something like that?
I'm thinking of like oxidation reduction, but I don't know if it's in the right thought process.
Yep, that's the right thought process.
Is but like I guess carboxylic acids like I guess I'm thinking of bonds to oxygen, but it could also be just bonds to hydrogen. So you're reducing it because you're increasing the bonds to hydrogen
Uh-huh. So
of
big
oxygen to hydrogen.
so say that again.
You're increasing the bonds of oxygen to hydrogen.
Uh-huh. So you're basically taking um the so yeah, so for the so yeah, so you're essentially taking an ester. So the carboxylic acid derivatives, do you remember what they were?
Yeah, I need to review that. I actually have a tab open with that.
Oh yeah.
Um,
So
um, so
yeah.
there's anhydrides, there's esters, there's amides, there's um
Yep. You
I
said
don't know.
yeah, so
Aldehydes probably.
oh yeah, no. So you'll have so basically if you just think of a carboxylic acid and you can just think of things that would replace the hydroxyl of this.
Okay.
So it can be a chloride, like an acetyl chloride here, which is super reactive. It can be an anhydride like this if you had like, two um uh carboxylic acids binding. You could have the amide and then you can have the ester as well. And the reactivity will be like in order of decreasing reactivity. Acid chloride, which is the most reactive, followed by anhydride, followed by esters, and then lastly will be amides. So, okay. So yeah, I was thinking of that too. Um, except it seems like what's happening here is um that I think it's breaking the I think it's actually acting as um just a base, I think. But but okay, so let's just say that okay, whatever as long as we know that we're changing an ester into a carboxylic acid. So that's how we get compound two. And then, we have compound three, which has doesn't have the aromatic R groups. Um, and then I guess the multiple arrows means that they're using more than one of compound three, perhaps. But uh, whatever happens to compound three, I don't know what these arrows. Wait,
Or like multiple reactions.
yeah, but I don't know what the reagent would be here. But okay, whatever. So that causes compound four to happen, which means that it seems like, an aromatic thing is added. And then when we add compound two and compound four with DCC, which they show us, we get this big monstrosity here with the compound two part here, compound four part here.
Mm-hmm. Yep.
So what seems to have happened is, I think, maybe this attacked here, that went up, this came back down, and then this OH came off to make that amide in a dehydration synthesis reaction, right? So, and we just get analogs, which are compounds five through eight. So, okay.
Um, so the researchers studied the analog structure activity relationship and antimicrobial activity against the gram-negative bacteria E. coli and the gram-positive bacteria. Oh wow, we anticipated this with the peptidoglycan.
Yeah, that's the
Yeah.
buzzword stuff that I talk about. Like there's all we're all you want your brain to be trained to look out for certain buzzwords to expect what's coming later. Yeah.
And the gram-positive bacteria S. aureus. Ampicillin, a penicillin derivative used to treat illnesses brought about by gram-positive and gram-negative bacteria, was used as a control. The minimal inhibitory concentrations necessary for the compound to inhibit growth and kill 100% of the bacteria are shown in Table 1.
All right, let's talk a bit about this MIC 100 thing. Um, is it proportional to like strength of killing bacteria or inversely?
Um, Let me think about it. So the smallest amount to kill
Mhm.
bacteria. So the smaller number you have of this MIC 100, the easier it is to like kill your bacteria.
Mhm.
So your what was your question again?
Oh yeah, the
Like
proportionality of MIC 100 to, I guess, strength as an antibiotic.
so the lower, so it's inversely proportional.
Good, good, good. You'll see that for like a lot of things. Like there's like lethal dose for 50% of the population. There's like even KM, right? Because that's substrate concentration at one half of V max. Uh, it's going to be an inverse relationship because if something is stronger at doing what it's doing, in this case being an antibiotic, and you need less of it to do this to kill the same amount, yeah, it's an inverse proportion. Good. Okay, and then we have a table with different type. Okay, so they're using penicillin derivative here, and then we have E. coli, which is gram negative. We have staph, which is gram positive, and we're measuring, yeah, the MIC 100 in micromolar, and what we see. So tell me what we see here.
Um, Seems that like the gram positive is uh stronger,
Okay,
just because the values are a lot lower than for the E. coli.
okay. So,
5, 6, 7, 8 are these
uh-huh.
different substrates. Yes. And ampicillin is a control.
Yeah, so the ampicillin, let me, is that a negative control or a positive control?
Uh, it's an antibiotic, and these are supposed to be antibiotics as well, right?
Just the
5 through 8. Sorry.
just the ampicillin.
Yes. It's positive control
Yep. Why?
because we know it's an antibiotic and that it works.
Yeah, we know that it works for gram positive and gram negative. So when we use it as our control, we are expecting to see some type of, some type of value for MIC 100. And it seems like, yeah, the MIC 100 for the E. coli is 69, and for the gram positive one, it's 2.9. So it's ampicillin works like, 20 times better for um, the gram positive compared to the gram negative E. coli, right?
Yeah.
So, okay, good. Because we talked about how MIC 100, if it's smaller, it's better. It's stronger at being able to do its job. All right, and then we have the variants or whatever with the 5, 6, 7, 8, and we see that for that the MIC 100 for E. coli goes up substantially, which means that it's no longer working very well. Um, and for the gram positive one, it's like going down slightly, so that could be working better in some of these analogs. But okay, you can continue.
The penicillinic acid analogs were tested for their effect on mammalian cell viability because toxicity to cells is also an important factor to consider for potential drug candidates.
Okay.
The general acceptable level of cell viability for a drug candidate is 70%. These results are shown in figure 2. Okay. So like you don't want to kill all your cells when you use this.
Mm-hmm.
Human cells.
Yep.
Uh, so they're looking at 3 different doses. Um, from lower to higher dose and cell viability. Does
Uh-huh.
that make sense?
Yeah.
Is this the dose
Uh-huh.
of the acid analogs? Okay.
Yeah, yeah. So we want to, so anytime you have like a graph or chart or some or figure or whatever with like two different types of information, um, I would just do it one by like one. So like like because either we evaluate each for the differences for these different concentrations, or we evaluate each keeping one of the concentrations constant, right? So I'm just going to
Mhm.
evaluate each keeping it constant. So like I'm going to just do it for 1 micromolar. So compound 5, it's around here. Compound 6, it's pretty much same. Compound 7, it's higher. Cell viability is higher, which means that I guess it's not killing as much. Then 8 is pretty much the same as 5 and 6. So it seems like compound 7 produces more cell viability. And then I
Yeah.
would go through, yeah,
No, it was
yeah. And then I would go through the um each of them and compare the concentration. So for 5, it seems like as the concentrations increase, seems like cell viability increases. I mean, they don't give us any statistically significant stuff here. Um, but and these error bars like overlap. So, but since they're not mentioning anything about statistical significance, sure, maybe I'll say like, yeah, concentration will go up with cell viability for compound 5. Compound 6 would be the opposite. So here, maybe I'll write down like, okay, compound 5 would be in terms of cell viability. Compound 5 um would be proportional to concentration. So, I mean, I don't know. Let's just say like concentration. Um, Compound 7 decreases with concentration. Wait, I skipped compound 6. No, that was compound 6, not compound 7. All right, compound 6 inversely proportional to concentration because cell viability goes down as you increase concentration, right? Then you have 7, which goes down and then goes back up. So that's kind of weird and hard for me to put into this proportionality. Um, but I'll just leave it for now. And then compound 8 seems to be the same. So I'm going to put compound 8, comma, compound 6 because both of them, um, as their concentrations go up, the cell viability goes down. So, okay, that's pretty much what I'll do. And yeah, any questions with that? So for the most part, like with when it comes to these charts and data and stuff, on your first read, you're not going to spend too much time on it. You just want to kind of take away some vague idea of what they're trying to show you. Um, and then if they ask you questions about it, then you can go back. So it's kind of like the opposite of what I say for cars. For cars, I tell students like to not go back unless you really have to. But for this, with all this data stuff, a lot of times like either they'll ask you about the data and it would be easy to answer, or they won't ask you about the data at all. So on your first, run, I usually say like, especially if this is timed conditions, to spend like 15, 20 seconds um, on the figures and stuff. And then attack the questions. And then if you need to, you can come back. So yeah, I think that's all we pretty much needed to understand this passage so far. So,
Yep.
okay, let's look at this question. So it says the synthesis of compound 1 begins with the nucleophilic acyl substitution of a carboxylic acid derivative um, with methanol under reflux conditions. Okay. This reaction forms a derivative of butanoic acid, where carbon 4 is a methyl ester. Which structure was most likely the carboxylic acid derivative used as the reactant in the nucleophilic acyl substitution? Okay. How should we go about this?
So I guess they're it's like this is the compound 1, so this is like how they made compound 1. So this is what we have to refer to.
Okay.
So it says that they did a substitution reaction of a carboxylic acid derivative with methanol
Okay.
under reflux conditions. I'm confused. I don't really know what they mean here.
Oh, okay. So,
Yeah,
uh-huh.
I don't know.
So, are you saying just the reflux conditions part?
Yes.
Okay. So that essentially just means that um, well, what's acid reflux?
Like acid going the
Mhm.
opposite way it should go.
Yeah, right. So reflux is essentially like if you like boil some mixture and you condense the vapor back into the liquid. So this way you can have um oh, and then the vapor that turns back into the liquid will go back into the vessel or the glass that you put the reaction mixture into initially. So essentially what this means is just that you can conduct a uh like a chemical reaction uh with high temperature, which can help increase the rate of that reaction. So that's what the reflux is. Um, what does this RT here mean?
Being room temp.
Yeah, good, good, good. So So yeah, that's this compound. That reaction is not reflux, but yeah, reflux. Just imagine that being like a way to make it so that, um, yeah, that you can have enhanced reaction. But okay, continue with what you were thinking.
So you have one of these derivatives
Hmm.
with methanol, which is
Hmm.
an alcohol with a methyl attached. OH with a methyl attached. I guess high heat, maybe high pressure, I don't know. A derivative, and you have forming a carboxylic acid, a 4-carbon carboxylic acid, where carbon 4 is a methyl ester. Uh, so an ester, uh, carboxylic acid attached to oxygen, and then a methyl group.
So,
Uh, yeah,
huh?
you were going to say something.
Yeah. So the carboxylic acid derivative, they don't tell us, so I wrote that as X. Then I added the methanol. I mean, I guess I just wrote ROH to mean like, an alcohol in general. But I added that. And then the product should be compound one. And then this derivative of butanoic acid, where carbon 4 is a methyl ester. So what does that look like? One, how many carbons is in the but part?
4.
Mm-hmm. One, two, three, four. And then, so if this used to be this, which is butanoic acid, um, and carbon one, carbon two, carbon three, carbon four, what they're doing is they're turning it into a methyl ester, right? So one,
Uh, could we review that just a sec? Wouldn't you start counting the carbon from the carbonyl carbon?
oh yeah, yeah, you're right. So let's do that. One, two, three, four. Yep.
Carbon 4 is a methyl ester. So are they referring to in this same molecule, carbon number 4 would be a methyl ester. So you would have, but that does that make I don't know.
Hmm. Yeah, tell me what you're saying.
So I'm thinking like the reaction forms derivative of butanoic acid, where carbon 4 is a methyl ester. So you should have an ester on carbon 4, right?
Uh-huh. Yeah. So
Um,
I think the carbon four part, um, yeah, I'm not sure about the carbon four part, but the reason I wrote or drew the numbers in the first way was I was just thinking, okay, I know that this is a carboxylic acid derivative, and sorry, this is a type of carboxylic acid, and to make a derivative that's an ester means that we're gonna just essentially turn it into this, right? Oh wait, no, sorry. There's an oxygen there. This, right?
Yeah, maybe. Yeah.
Mhm. So we I'm not worried too much about the carbon four part, but I know that the one of the products will be um a derivative of butanoic acid, which is this, and then it turns into a methyl ester. So, that would be taking the carboxylic acid functional group and turning it into the ester functional group.
Okay.
Yeah, just because, so essentially for acid derivatives, right? I guess like I should talk a little bit about that. Um, Basically, what you can have will be, let's see. Um, so okay, you could have basically, um, or let me see if I could just do. Okay, so just in general, right? You can have a carboxylic um acid, and you can add like SO um Cl2, which would, look like this. Oh wait, what am I talking about? Sorry, these are chlorines, like that. So, uh, so what can happen here is, yeah, what do you think can happen here?
Um, I guess this hydrogen, uh, I don't know what would happen.
Okay, so what you essentially will have happen is, um, so yeah, typically we think of carbonyl groups as being like, the ideal um electrophile, but we
Yeah.
have this sulfur in, so we have something similar to a carbonyl group, except the carbon is replaced by a sulfur, but you have these highly electronegative chloride substituents, which act as electron withdrawing groups, which make this dipole even more so of a dipole. So that would mean that essentially that this um could attack, oops. So that could mean that this can attack here and form a bond with that. And eventually this gets kicked out, and you just have the fluoride part that's there.
I see. So when you drew that, is that the oxygen attacking or
Yeah,
okay.
because yeah, that is going to be like it's a little weird because we usually have that carbonyl carbon being the one that gets attacked, but compared to the SOCl2, um, the carbonyl is going to act less as will act less as an electrophile and more as a nucleophile, just because the sulfur of SO Cl2 has those electron withdrawing groups. So, yeah, the actual mechanism I can get for you, but the idea is that it produces um, an acid chloride. So here, let me get this. Okay, I'm going to put this image in the chat here. So that's just the mechanism to make the acid chloride. Um, and once you get the acid chloride, this guy, it's super, super, super reactive, as you would imagine, due to the electron withdrawing group of the chloride. Now that chloride, the acid chloride, you can use that as the reactant to make the rest of the um, carboxylic acid derivatives. Um, but you can also just continue to use carboxylic acid derivatives. So for example, if you had like two carboxylic acids, you would get your anhydride. But if you had an acid chloride plus a carboxylic acid in base, you can also get an anhydride. But essentially, I can send you like some type of like I guess like list of like the different carboxylic acid derivatives and stuff. But just for this problem, any type of carboxylic acid derivative will mean that the this OH part is going to get replaced. Okay.
Yeah.
It can get replaced with a bond to a chloride. It can be replaced with a, or it can keep its oxygen and just have another thing attached to that, which will be the anhydride. It can be an ester, which means the O will still be there, but the H will turn into something, will turn into like a methyl, kind of like that. So yeah, so essentially what we're having here is we're having this turn into that. Yeah. I don't know, the numbering, you know, I don't know about like I guess I'm not putting too much attention on that one being carbon four. Um, so but I know at least that the
Yeah.
butanoic
It's
acid, yep.
yeah, it's good to think that like the majority of these reactions will be like substitution reactions to like find create other like derivatives.
Mhm. Yep. So okay, so we see that we have this over here, right? So our product, our additional product here is going to be this. And then here I might as well, I wrote ROH, but I might as well just write like, you know, um, CH3OH to be the methanol. So we see that, so okay, we have some structure that we add methanol to under reflux conditions, heat and stuff like that. And it gives us compound one, and it also gives us this butanoate, I think, or yeah, methyl butanoate, I think it's what it's called. So now we just have to figure out what that starting compound was. So we know that compound one looks like this. So what could, you know, what could we get, or what could we start off with, I guess?
Um, this kind of looks like this is what I'm thinking about now.
Okay.
but yeah, I guess I'm still struggling to see like how this is related to this.
Mhm.
In the question stem.
Yep. So,
So is this like another product or is this like before they create compound one?
oh, yeah, it's before they create compound one.
Before they create compound one,
Mhm.
they have this. So this is okay.
They have what? What are you saying?
So this structure
Mhm.
is not like uh what is it? Like is it like an intermediate kind
Oh,
of
no, it's just a
but
product.
no?
It's just
Sorry?
one of the products.
One of the products.
Yep, the products.
Um
Yeah, the products are compound one and the methyl butanoate.
and this is a method. Uh
Yeah, point to that again.
um
Mhm.
yeah. So my question is like the product of that reaction is compound one and this or like this then becomes compound one.
Oh yeah, so yeah, it's compound one plus that.
Okay. Okay.
Mhm. So yeah, so
I
now let's
see.
think about yeah.
So it has to be something that you can create like an ester plus something else. Sort of like how you cleave an anhydride and you have two carboxylic acids, is what I'm thinking.
Mhm. Yep. So yeah, they're talking about the nucleophilic acyl substitution of a carboxylic acid derivative with methanol under reflux conditions. So we know that so X is also going to be a carboxylic acid derivative, but it will be one that will have or be having its acyl group nucleophilically attacked by the ethanol, most likely here.
Yeah.
So what you can have is so let's imagine what can happen with the methanol for each of these things, right? So for instance, if I had a methanol here, it would like attack there and push that over there. This comes back and then this breaks off. Um, but we want something that will do something like that, but it will maintain the um essentially what we're looking at is like this is like our leaving group. Okay. Now, uh, so this over here would give us this as our leaving group, so that can't be it. This one here, well, we can have the alcohol either like deprotonate this carboxylic acid end over here, or it can attack, this, which would mean that this bleeds, right? But none of this seems to be causing anything. We what we want is, I think a better way of kind of like understanding this um, is that we have okay, one, two, three, four carbons here. We have one carbon here. Um, compound one. Um, I mean, I guess there's a lot of carbons there, but I guess what I would think about is what can be something that uh, could have its which of the choices could you get four carbons like removed from and replaced by one carbon, I guess. So like something like this where we have like one, two, three, four, right? We can have this guy. just attack one of these carbonyl groups, which will force, the electrons from the double bond onto this oxygen. But when it comes back down here, it'll kick off a leaving group. In this case, it'll kick off that bond, which will open up that ring, right?
Yeah.
And when you open up that ring, you would get like, so there's 4 carbons here. So you would attach that with, you know, the one of the methyls here.
Yeah.
So essentially what you're going to be looking for is a carboxylic acid with a good leaving group that can be displaced by the methanol. So the like esters can be, or like the methoxy group can be a good leaving group, and that's something that choice A has. Because when this unravels, it would be essentially like something like 1, 2, 3, 4, something like that, right? So you're opening up that ring in this case. So yeah, if you basically take, so there's, I guess those are like the couple of ways to go over this. But what we're really trying to see is, um, for each of these choices, if you add methanol, how would it produce this methyl butanoate? So
Okay.
yeah, so that would mean, so okay, if we had CH3, methanol attack here, it would break apart the ring but it would leave the amine in the ring, right? I'm sorry, it'll break apart the ring, and you'll just have one end be an amine, right? But we don't have that in our end product, so that can't be it. And then here, similar type of deal, right? But this is already a chain that's so it's not going to be like resulting in anything, in a ring opening or anything like that. And it'll most likely like deprotonate this. I think that's what it would most likely do. But this already has a carboxylic acid and an ester, and we want something that uh oh, and in addition to that, yeah, I guess like we want to create that um ester bond after we do the reaction. So this already has that. So that's not going to work. So yeah, so essentially how to do this problem is understanding what they're asking, and they're asking that, or saying that the synthesis of compound 1 begins with the nucleophilic acyl substitution of a carboxylic acid derivative, we don't know which, with methanol. So I wrote that here. And this produces a derivative of butanoic acid where carbon 4 is the methyl ester. That's this one. And we know compound 1, I suppose, is, I mean, it's kind of like impossible for it to turn into that. So I think that's what they mean by begins. I think this is just the first step or something like that. So I don't think like this could be like maybe an intermediate for this compound 1. But uh but yeah, I think the best way to go about this is by looking at this product, and then we must think, what can we add methanol to, in which methanol will act as a nucleophile? So what can we act, and we know that also from they're telling us that nucleophilic, substitution with methanol. So what choice here can, if you had methanol, can methanol nucleophilically attack to cause this to leave as a leaving group? So
Yes.
that's where I would, yeah. So like for D, it would attack this carbonyl, but this would just result in this nitrogen attached to the methyl that would leave, right? So that would have to be in our byproduct here, but it's not. So D is out. Then here we would want something. So let's see, 1, 2, 3, 4, uh, you know, carbons here. Wait, five carbons there. But the carboxylic acid is attached to the ester, and we want like I guess something that won't have both of these things because like basically if you just had this carboxylic acid, the methanol could act to deprotonate it just because the acid will behave like an acid. So I think that yeah, that won't work. And then B, again, if it does this, it'll just open this up. So, you would get like NH, then 1, 2, 3, 4, 1, 2, 3, 4, and that's where the carbonyl would be. So this will open up the ring, but you would end up getting, something with a nitrogen in it, which we don't get. So essentially, that could be a way of going about it, getting rid of the ones with nitrogen. But yeah, this one over here, it's going to attack there. It's going to break this ring open, and that's what this would look like. Because if you took this and you reformed the ring like this, whoops, like let's say that you did like the reverse of whatever, um, this would then or this could attack like something over here. But I mean, it would be before it turns into the ester. But generally speaking, yeah, just understand what the question's asking and then just try to figure out what would happen if you added methanol to each of these choices and would it result in something that would look like the uh this methyl butanoate.
Okay.
Yeah.
Good.
Yeah, I think the four thing probably is what made most people choose this because this works with the type of naming that you mentioned, right? Like if this is 1, 2, 3, and 4, or rather, the other way around, if this was 1, 2, 3, and 4, then it would make sense that this fourth carbon is the methyl ester, right? So I think that's
Yeah.
why most people chose that. So I don't know why they would say carbon 4 is a methyl ester because, yeah, maybe in this process here, it switches, but not completely sure. But yeah, like I understand why most people chose C. Yeah.
Yeah.
Yep.
All right. I think I should probably get home because it's getting pretty late and
Oh
I'm still
yeah.
in lab.
Let's track of time.
Yeah.
So,
Yeah.
okay, yeah. So for these Orgo stuff, let's see what I can think of. Because you had more questions for this, right? Or for the
Uh,
passage, I think.
yeah.
You can like
I
email.
I did the other ones. The other ones were
Okay, makes
easy.
sense.
I just haven't done this one. And nor this one. So I haven't attempted.
Got it, got it. Yeah, if you have like a list of, oh yeah, I'll send you like a resource for like the carboxylic acid derivatives and stuff. Um, but yeah, we can talk more about like Orgo next time. But okay, awesome. So yeah, any other questions for today?
Yeah. Um, no, but actually tomorrow I think I would like that. Like if we could just go over like
Mhm.
very basic, like nucleophile, electrophile, and like and
Uh,
maybe SN1, SN2, E1, E2, and like basic reactions
look
for
at
Orgo. That would be great.
did you take a look at the Orgo PDF I have in the shared drive?
No, I haven't.
All right, check that out because I go over like yeah the basics there. Um, so yeah, take a look at that, and then yeah, tomorrow we can continue.
Okay, sounds good.
All right, take care.
Bye.
All right, see you tomorrow. All right, I just wanted to go through this again. So really quickly, let's make sure we understand the question. So it's saying that the synthesis of compound one, this guy, begins with a nucleophilic acyl substitution of a carboxylic acid derivative with methanol. Now, we don't know what this carboxylic acid derivative looks like. I'm just going to use X to express that. Plus the methanol, so that'll be essentially like CH3OH yields, and they're telling us that it forms a derivative of butanoic acid where carbon 4 is a methyl ester. So prior to this, I was equating the two, like I was essentially writing down that butanoic acid would be 1, 2, 3, 4 with that. And they're telling us that this reaction causes it to have a methyl ester on its carbon 4. So I mistakenly put that as this, replacing the carboxylic acid OH group with the methoxide group. But they're telling us carbon 4 is the methyl ester. So if we numbered these carbons, this carbon at the end is the fourth carbon, and that's the carbon that should get the um, ester group attached to it. So let's redraw that. So this should just then be something like well, I'll make the I'll make it so that the carboxylic acid is on the left. So like this. So this is 1, 2, 3, and 4, and we can see that, and this is where the methoxide will bind to. And you see how the first carbon is where the carboxylic acid is, and the second, or rather the fourth carbon, is where the new methyl ester is. So this actually is this derivative product. So essentially our product will be, it won't be compound one since they mentioned that this just begins with this step, but it'll be some, intermediate of compound one that we shouldn't really be focused too much on. However, we know that another product will be this compound. So you can just draw that again here. And yeah, so this has a carboxylic acid end to it and also an ester end to it. I'll just write down ester here. So we need to figure out what original carboxylic acid derivative would, upon adding the methanol, which, by the way, this acts as a nucleophile. In other words, a Lewis base, in other words, a lone pair or an electron pair donor. So let's evaluate these, like each of these, right? I mean, there's two approaches. We can evaluate each of them, or we can use our knowledge of carboxylic acid derivatives. But let's start with just trying out the methanol for each of these compounds. So let's say we start off with this one. So I'm just going to write like the methanol here, and this should, I'll use light green. This should attack this, forcing the electrons momentarily to move there. But when they come back to reform the double bond, they'll kick off that amide nitrogen, which will kick off the amine over here. And that would just give us a product that would look like, oops, something like this. Okay, now this isn't fine and all, but if we count the carbons, right, we have 1, 2, 3. I mean, we also have this carbon, but it's a three carbon chain, 1, 2, 3. And we want our original compound to have um, enough for, one, two, three, and four. We want it to have four carbons, and we don't get that here. We only have three carbons here, three carbon chain at least, right? I guess total in, if we count this, it would be for the four carbons, but yeah, we're not going to, uh, even if it did have the right amount of carbons in a chain, the nitrogen should be in our product over here. So we don't have a nitrogen in our product, so this can't be it. And for the same reason, choice B can't be it, right? Because here it will the I'll draw it. The methanol will attack this, pushing this over here, bringing this back here, and then breaking this bond. And that would result in, opening of the ring, but you're still going to have a nitrogen there. And we don't have the nitrogen in the end product that they're telling us. So this should not be it either. Now, C seems like a popular choice because 58% ended up choosing it. And C happens to be this over here. It happens to be the derivative that forms. So yes, this is indeed the one of the products that we get. Um, but we're being asked what carboxylic acid derivative is used as the reactant. So what can cause the formation of C? Because we know C can't be it. So let's take a look at A. So A, I didn't catch it at first, but A is actually so so A is actually a cyclic amide. A cyclic anhydride. So first of all, I'll just draw like a generic anhydride. So something like this, right? Where we have three oxygens and the central oxygen is connected to two carbonyl carbons, which have their own oxygens. So if you just imagine this as a ring, which means we're going to connect to this part and this part, right? That would just be this molecule over here. So it would be essentially this O here, and then the carbonyls here, and then um, the other this end over here and this end over here are here, and then they can close the ring like that. So this is a cyclic anhydride. Now, if we take our methanol, this will attack the carbonyl carbon, again, momentarily moving the electrons from the double bond to the oxygen. And when it comes back to reform the double bond, it will break this bond. Oops. It'll break this bond, thereby opening up the cyclic compound. So when you have that opened up, what does it look like? It's going to look like, um, well, it's going to look like this. Because what you have happen is, I mean, I can go into, um, I guess, like the mechanism of it, but all in all, it should make sense that this, if it opens up, I guess I'll draw it. So it'll open up like this. Let's see. So that's the original molecule, and then it will turn into, so if the methanol attacks here, this one will open up with, oh, well, not open up, but a double bond will turn into a single bond with a negative oxygen. And it would also be bound to the methanol, which would give it a plus charge there. And what can happen here is this negatively charged oxygen can bind to or get protonated here. And as that happens, this can get deprotonated, which will then give us a product that will look like this, where we have this, and then this is an OH here, but there's also that OCH3, OCH3. So we have both of these guys. Now we only want one because we want meaning we only want one oxygen because we need to recreate the well, I shouldn't say that. I should say that we don't want this OH group. We want this OH group to turn back into a carbonyl so we can have this OCH3 group act as an ester. So basically that's what we want to have happen. So we can have this get deprotonated and reform this double bond here to get our, oh, and it will also open up the ring to give us, all right, it was getting pretty messy, so I just made this white space here. So let me draw this again. So let's have our choice A molecule. So I'm going to draw it here. That. And we're adding our methanol. And what happens is this methanol will attack one of these carbonyl carbons, forming a bond with it, pushing the electrons from this double bond to this oxygen. So what happens then is you'll have an oxygen with a negative charge. You'll have this methanol, like this, attached to it as well, producing a positive charge here. And then we have the rest of the molecule here. So what happens here is that, well, this negatively charged oxygen is going to deprotonate this hydrogen from the methanol, and the electrons that form this bond will go, oops, will go towards the oxygen here, like that. Whoops, I keep doing that. Like that, which would eliminate this double bond here. I mean, sorry, will eliminate this positive charge here, as well as the negative charge here. So this then becomes something like this, where we have the OCH3 as well as the OH, right? The charges are gone now. And then the rest of that. So, okay, seems like we have some type of, I believe this is like I think a ketal or an acetal of some sort. But we're not going to leave it at that because the OH group is always super electrophilic. I'm sorry, nucleophilic. So what can happen next is, it can essentially uh, have its electrons moving over to here, that bond over here, and like to essentially reform that double bond. And it would have to break this bond here. I should have done this in light green. So this comes back here, reforms a double bond. This breaks off as a leaving group. And so the next thing that we get is, oh, and since this bond breaks, we are cleaving the ring. So the ring is going to open up. So so at one end it will be like, something like this. Um like this OH here will have a positive charge because it has a double bond now that's being created. And the other thing is this methoxide here. So that's just the OCH3. And then this ring is opened up and it has 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. And then the other side is just this O minus here, which is this oxygen atom here. I'll label it. So this oxygen I'm putting in orange is this one in orange. Okay, now, this obviously can't be the way it is. So this proton is going to get taken away by that negatively charged carboxylic acid or carboxylate end. And this will go here and it will get rid of this positive charge here to give us our OCH3. This turns into the double bond or the carbonyl bond. Oops. Which would then give us that. And this is the this is the mechanism for adding methanol to a cyclic anhydride. And it's the fact that it's cyclic doesn't make too much of a difference. I mean, if you had a regular anhydride, this would just break apart into, a carboxylic acid and an ester, something like that. It has two separate compounds because it's not a cyclic structure. But if you're doing it for a cyclic structure, it'll break apart the ring, producing one structure that contains both the carboxylic acid that we're expecting as well as the ester that we're expecting. So yeah, so that's the mechanism for that. Hopefully this was helpful. And yeah, that's it.